Welcome all students to the course of Data Communication Networking. We are discussing the Unit 2 physical layer, the data and the signals. The same topic is continued in this session. Up to now, we have seen this data and signal, analog and digital data and signals, periodic and non-periodic signals, sine wave, wavelength, time and frequency domain analysis, composite signals and bandwidth. In this session, we are going to continue the same topic with different fundamental terms. So, digital signals, in addition to being represented by the analog signal, the information can also be prepared or presented by the digital signal. For example, a 1 can be encoded as a positive voltage and a 0 is a 0 voltage. The digital signal can have more than 2 levels. In this case, we can send more than 1 bits for the each level. A particular figure shows the 2 signals, one with 2 levels and other there is a 4 level, just like this 1, 2, 3 and 4. So 4 layers are there. What 4 levels are there? We send 1 bit per level is a part of the figure and the 2 bits per level in the part of B of the figure. In general, if a signal has an L levels, then each level needs log 2 base L bits. Fine. So in this session, the following topics we are going to see: bit rate, bit length, digital signal as a composite analog signal, application layer for the same. Let's have an example. So a digital signal has an 8 level. How many bits are needed per level? We can calculate the number of bits from the formula. The number of bits level is equal to log base n is equal to 8 levels. So the answer is 3. A digital signal has 9 levels. How many bits are needed per level? So we calculate the number of bits by using the formula, and the figure is also displays the same. Fine. Next is bit rate. The most digital signals are non-periodic, and thus the period and the frequency are not appropriate characteristics. Another term, bit rate, instead of frequency, is used to describe the digital signal. A bit rate is the number of bits sent in a 1 second expressed in the bits per second, or we can say BPS. The figure shows the bit rate of the 2 signals over here. Fine. So in this figure, the bitrate is 8 bits per second, and in this figure the bitrate is 16 bits per second. Fine. So we can say that each second have 8 bits and each second have 16 bits. Let's have an example. Assume we needed to download a video or a text document at the rate of 100 pages per minute, and what is the required bitrate for the channel? So the page is an average of 24 lines with 18 characters in each. If you assume that the one character is required 8 bits, then the rate is 100 into 24 into 80 into 8 is equal to 1.636 Mbps. A digitalized voice channel, as we will see in the chapter number 4, that is made by the digitalizing 4 kHz bandwidth along the analog voice signal. We need to sample the signal at twice at the highest frequency, the 2 samples per hertz. We assume that each sample is required 8 bits. What is the required bit rate? So the bit rate can be calculated as 2 into 4000 into 8 is equal to 64 kbps. So what is the bitrate of the high definition TV? Recently we are using the SD TV in our daily use. So the SD TV uses the digital signal to broadcast high quality video signals. Then SD TV screen is normally a ratio of 16:9, in the contrast to the 4:3 for the regular TV, which means that the screen is wider. There are 1920 into 1080 pixels per screen, and the screen is renewed 13 times per second. The 24 bits represents the each color pixel. Then we calculate the bit rate as all the multiplication can be done. Then we can say that it is a 1.5 Gbps. So the TV station reduce this rate to 20 to 40 Mbps through the compression. So compression is required. Bit length. We discussed the concept of the wavelength for the audio signal, the distance one cycle occupied on the transmission medium. We can define something similar to the digital signal is a bit length. The bit length is the distance one bit occupies on the transmission medium. Means the bit length is equal to the propagation speed into bit duration. Okay. One of the good concept is digital signal is a composite analog signal. So our digital signal can be represented as a composite analog signal. Based on the Fourier analysis, a digital signal is a composite analog signal. The bandwidth is infinite, as you may have guessed. We can intuitively come up with a concept that when we consider a digital signal is in time domain, comprised connected to the vertical and the horizontal line segmentation. A vertical line in the time domain means the frequency of infinity, and the horizontal line of the time domain means the frequency of 0. Going from the frequency of the 0 to the frequency of the infinity implies all the frequency between the part of its domain. The Fourier analysis can be used to decompose a digital signal. If the digital signal is periodic, which is rare in the data communication, and the decomposed signal as a frequency domain representation with the infinite number of bandwidth and the discrete frequencies. If the digital signal is non-periodic, then the decomposite signal still has an infinite bandwidth, but the frequencies are continuous. A particular figure shows the periodic and the non-periodic digital signals and their bandwidth. Note that both bandwidths are infinite, but the periodic signal has a discrete frequencies while the non-periodic signal has a continuous frequencies. Fine. So if there is a discrete, is our continuous. So how to transmit our digital signal with the help of the medium? So the transmission of the digital signal come into the picture. Our previous discussion said that the digital signal, periodic or non-periodic, is a composite analog signal with the frequencies between 0 to infinity. For the transmitter of the discussion, let us consider the case of the non-periodic digital signal similar to the ones we encounter in the data communication. The fundamental question is, how can we send a digital signal from point A to point B? We can transmit the digital signal by using one of the two different approaches, the baseband transmission or broadband transmission using modulation. Means when a broadband transmission is there, there is a modulation. In the first, the baseband transmission, the figure shows the baseband transmission. The baseband transmission means sending a digital signal over the channel without changing the digital signal to the analog signal. Means a particular digital signal is sent in its original form. So we can say that it is a baseband transmission. So there is no change of the form of signal in a transmission medium. So we can say that it is a baseband signal. So a digital signal is a composite analog signal with an infinite bandwidth. a baseband transmission requires that we have a low pass channel and channel which the bandwidth starts with a 0. This in the case we can have the dedicated medium with the bandwidth continuously only one channel. So it will have only one channel. For example, the entire bandwidth of the cable connecting to the two computers is in one single channel. So it occupies all the time. As another example, we may contact the several computers to our bus, but not allow more than 2 stations to communicate at a time. Again, we have a low pass channel and we can use it for a baseband communication. A figure shows the two low pass channels, one with the narrow bandwidth and another with the wide bandwidth. We need to remember that the low pass channel with an infinite bandwidth is an ideal, but we cannot have such a channel in a real life. However, we can get close. So figure shows the low pass channel with a wide bandwidth, low pass channel with a narrow bandwidth. So let us study some cases of baseband communication, a low pass channel with a wide bandwidth and one with a limited bandwidth. If we want to preserve the exact form of non-periodic signal within vertical segments, the vertical and the horizontal segments are horizontal. We need to send the entire spectrum of the continuous range of frequency between the zeros and infinity. This is possible if we have a dedicated medium with an infinite bandwidth between the sender and the receiver that preserves the exact amplitude of each component of the composite signal. Although this may be possible inside the computer between the CPU and memory, and it is not possible between the two devices. Fortunately, the amplitudes of the frequencies at the border of the bandwidth are also so small that they can be ignored. This means that if we have a medium such as a coaxial cable or the fiber cable with a very wide bandwidth, the two stations can be communicated by using the digital signal with a very good accuracy as shown in this figure. Right? Note that F1 is close to 0 and F2 is very high. F1 is 0, F2 is very high. So the shape of our received signal is which is nearly same to our input signal. Fine. Although the output signal is not exact replicates the original signal, the data can still be deduced from the received signal. Note that although some of the frequencies are blocked by the medium, they are not critical. The baseband transmission of the digital signal that preserves the shape of the digital signal is possible only if we have a low pass channel with an infinite or very wide bandwidth. Let's have an example. An example of the dedicated channel where the entire bandwidth of the medium is used as one single channel is a LAN. Almost every wired LAN today uses the dedicated channel for the two stations communicating with each other. In the bus topology, LAN with the multiple connection, only two stations can communicate with each other at each moment of time sharing, and the other station need to be refrain their standing data. In the star topology, the LAN, the entire channel is between each station, and the hub is used for the communication between these entities. The LAN will be studied in this course in the later chapter. Second is a broadband transmission using modulation. A broadband transmission or the modulation means changing the digital signal or analog signal for the transmission. The modulation allows user to bandpass channel, a channel with a bandwidth that does not start from 0. Fine? And this type of channel are more available than low pass channel. Figure shows the bandpass channel. It shows the bandpass channel, means it's starting not from the 0. Note that the low pass channel can be considered as a band pass channel with a lower frequency starting with 0. Fine. So it can be shifted over there, then we can say that it is a low pass. But the bandpass is not a low pass. If the available channel is a bandpass channel, then we can send the digital signal directly to the channel, and we need to convert the digital signal into the analog signal before the transmission. By understanding this, we have an example. Figure shows the modulation of the digital signal. In figure, a digital signal is converted into the composite analog signal. We have used the single frequency analog signal called the carrier, and the amplitude of the carrier has been changed to look like a digital signal. The result, however, is not a single frequency signal, it is a composite signal. At the receiver, the received analog signal is converted to the digital, and the result is replicated at our have been seen. It is the same to our transmitting signal. So a modulation process has occurred at the transmission, and the demodulation has been occurred at the receiving. An example of broadband transmission using the modulation is sending of a computer data through the telephone subscriber line, and the line connecting to the resident to the central telephone office. As in the early stage of internet or early stage of internet connection, that we are using the dial-up connection. These lines installed many years ago and are designed to carry voice analog signal with a limited bandwidth, frequencies between 0 to 4 kHz. Although this channel can be used as a low pass channel, and it is normally considered as a band pass channel. One reason is that the bandwidth is so narrow, 4 kHz, and that if we treated the channel as a low pass channel and use it as a baseband transmission, the maximum bitrate that can employ is only 8 kbps. So the solution is to consider the channel as a band pass channel and convert the digital signal into the computer to the analog signal and send it to the analog signal. We can install the two converters to change the digital signal to the analog and vice versa at the receiving end. The converter in this case, called as a modem, modulator or demodulator, we will see in the later in the chapter. Next is transmission impairment. Signal travel through the transmission media which are not perfect. The imperfection causes the single impairment. This means that the signal at the beginning of the medium is not the same as at the end of the medium. What is sent, not is received. Three causes of impairment are attenuation, distortion, and noise. So that 3 points we are going to see: attenuation, distortion, and noise. First is attenuation. Attenuation means a loss of energy. When a signal, simple or single or a composite, travels through the medium, it loses some of its energy in the overcoming the resistance of the medium. That is why a wire carrying electric signal gets warm, if not hot, after a while. Fine. Some of the energy signal in the signal is converted to heat. To compensate their loss, the amplifier are used to amplify the signal. A figure shows the effect of the attenuation and the amplification. So our original signal is there, the transmission medium is this. By transmitting from point 1 to 2, some value is changed, then it can be said that it is attenuated because the main value is different from this point. Then amplifier will amplify the value, then we can say that it is nearly equal to our transmitting signal or our original signal. Decibel. To show that a signal has a lost or gained strength, engineers use a unit called as a decimal. The decimal, dB, measures the relative strength of the two signals or one signal at a two different frequency point or two frequent points. Note that the decimal is in negative if the signal is attenuated and positive if the signal is amplified. So the equation is dB is equal to tan log base 10 P2 upon P1. Variable P1 and P2 are the powers of the signal at the point 1 and 2 respectively, and note that the sum engineering book defines the decimal in the terms of voltage instead of power. In this case, because of the power is proportional to the square of the voltage, the formula will be dB is equal to 20 in log base 10 V2 upon V1, which can be expressed in dB in terms of power. So it is an example of 1 dB. Suppose the signal travels through the transmission medium and its power is reduced to 1/2. This means that P2 is 1/2 P1. In this case, the attenuation power of loss can be calculated as 10 log 10 P2 upon P1. Then we can find it is a minus 3 dB. So the loss is 3 dB is equivalent to the losing the 1/2 the power. A signal travels through an amplifier and its power is increased to 10 times, then this means that the P2 is equal to 10 P1. In this case, the amplification or gain of the power can be calculated as 10 log base 10 P2 upon P1. We can say that it is a 10 dB. One reason that engineers use the decimal to measure the changes in the strength of the signal, that is that the decimal numbers can be added or subtracted when we are measuring the several points cascading instead of just two. As we can see in this figure, that signal travels from the point to A from point 1 to point 4. In this case, the decimal value can be calculated as dB is equal to minus 3 plus 7 minus 3 plus 1. How? Minus 3, the transmission medium contains minus 3 dB loss. Over here, the amplifier used, so plus 1 is there, and plus 7, and plus 7 is there. Then a particular transmission medium has a minus 3 dB loss. So overall, it is a overall signal is a gain in power, plus 1. Sometimes a decimal is used to measure the signal powers in the milliwatts. In this case, it is referred to the dBm and it is calculated as dBm is equal to 10 log base 10 pm, where the pm is the power in milliwatts, and the calculated power of the signal with dBm is equal to minus 30. We use the equation and get the answer pm is equal to 10 raised to minus 3 milliwatt. The loss in the cable usually defined in the decimal per kilometer or dB by kilometer. If the signal at the beginning of the cable with a minus 0.3 dB by kilometer has a power of 2 milliwatt, what is the power of the signal at 5 kilometers? So the loss in the cable in the decimal is 5 into 0.3, because 5 kilometers is there, then the minus 1.5 dB. Then we calculate the power as dB is equal to 10 base 10, P2 upon P1 is equal to minus 1.5, then P2 upon P1 is equal to 10 raised to minus 0.15 is equal to 0.71. The P2 is equal to 0.71 into P1, and P1 we have 2 milliwatt, then we can say that it is a 1.4 milliwatt. Another term, distortion. The distortion means that the signal changes its form or a shape. Distortion can occur in the composite signal made of the different frequencies. Each signal component has its own propagation speed through the medium and therefore its own delay in arriving in the final destination. The differences in the delay may create the difference in the phase if the delay is not exactly same as the period of duration. In other words, a signal components at the receiver have a phase difference from that they have at the sender. The shape of the composite signal is therefore not the same, and our figure shows the effect of the distortion on the composite video signal. So it is a computer signal sent, then the components of the phase are there, and at the receiver there is a slightly change in the shape of the signal due to the distortion. Noise. Noise is another cause of impairment. Several types of noise, such as thermal noise, induced noise, crosstalk, and impulse noise, may corrupt the signal. Thermal noise is the random motion of electrons in the wire which create an extra signal not originally sent by the transmitter. Induced noise comes from the source, such as motors or appliances. These devices act as a sending antenna and the transmitting medium acts as a receiving antenna. Crosstalk is the effect of the one wire on the another. One wire acts as a sending antenna and the another as a receiving antenna. Impulse noise is a spike signal with a very high energy with a very short time that comes from the power lines, lightings, and so on. Our figure shows the effect of the noise of the signal. It is our transmitted antenna, there is a transmitting signal, it is our noise, then our signal will become like this by adding this noise. So it is a different from our transmitting signal. One of the important terms, signal to noise ratio, SNR. As we will see later, that to find the theoretical bitrate limit, we need to know the ratio of the signal powers to the noise power. Means the signal to noise ratio, defined as the ratio between the average signal power to the average noise power. We need to consider the average signal power and the average noise power because this may change with time. Our figure shows the idea of SNR. It have a large SNR with noise, signal plus noise, low SNR. So in the low SNR, the signal is very, very different from our transmitting signal. Okay. SNR is actually the ratio of what is wanted to what not wanted. Means it is wanted, it is not wanted. And a high SNR means the signal is less corrupted by the noise, and the low SNR means the signal is less corrupted by noise. Because the SNR is the ratio of the two parameters or two powers, it is often described as a decibel units, SNR dB, which is defined as 10 log base 10 SNR. Let's have an example. A power of the signal of 10 milliwatts and the power of the noise is 1 microvolt. What is the value of SNR and SNR dB? The values of SNR and SNR dB calculated as the following equation. It is very easy to calculate the data from the given data. Another example shows the values of SNR and SNR of noiseless signal are infinity by putting the noiseless is equal to 0, so it will become infinity, and we can achieve the ratio in the real life, and it is ideal. So it is not achieved at our life. So up to now we have completed our session. It is a question for you. What we have seen: bitrate, bit length, digital signal length as a composite signal, application layer, attenuation, distortion, and noise. Write down in your notebook and send it back to me as per the given direction. Hope you understand this basic concept. Thank you and see you in the next session.